welcome to my new video. Now I'm going to show you the basics of the multiplexers and some IC integrated circuits that act as a multiplexer. So multiplexer is a combinational device that only chooses one input to the output. It has multiple inputs and only one output. But we choose input by this data selector. If a combinational device has two powered on the n inputs, there is n selectors. For example, here we have two on the first two inputs, then we're gonna have that one selector. If you have four inputs, that's two on the powered by the two, then we will have two selectors. Okay, so here is a simple one of two data selector. If the data selector, this data select is on a low state, the output is going to be A. If this data select is on 1, then the output is going to be B. Let me just simulate and run the program, as you will see now. Moment. Now you see that the output is the same as A, but it also is the same on B. But if I change the B, it won't change the output because the data select is on 0. So if the data select is 0, here this red square means that here is a high output, and it goes to the AND gate. If both inputs are 1, then the output is going to be 1. But now it's just 1 and 0. 1 and 0 is 0. 0 goes to the OR gate. 0 and 0 on the OR gate is 0 on the output. But if I change the A to the 1, you will see that here we will have the 1 on the output. 1 is going to be in the OR gate. 1 or 0 is 1 on the output. So, but if I click data select to put it on the high state, you will see the output goes to the B. The B is going to be the output. Now, why? Because here I have a not inverse gate. So here we have a low state. Low state goes here to the AND gate. AND gate there's 0 low level blocks the A input. So no matter what you do here, the output is going to be 0. So now if I put the data select on B, you will see that the output is going to be the same as B, because here we have a high input and the AND 1 and 0 is going to be 0, 0, and no matter what, 0 and 0 is going to be output 0, or 0 is output is 0. But when I change it to 1 and I change this, the output is always going to be B. So now I have 1 and 1, that is 1. Here I have 1 or 0, that is 1. So that is a simple one of two data selector. Okay, now here on my second circuit, I have a 4-line to 1-line multiplexer. I have 4 inputs, and then I will have 2 data selectors. If the S0 and S1 is 0, then this gate will be activated, because we have we have two high levels here, and it also depends on the A here. So if this is 0 and 0, that's like number 0, and that goes to the A, and it changes with A, as you can see. When I change B, nothing happens. When I change C, nothing happens. When I change D, nothing happens. If I put 1 on S0, the output is going to be equal to the B, as you can see. If I change A, nothing happens. Change here, nothing happens. let me just this is the schematic. It is kind of hard to read, but if you pause the video clip, you will see which one goes in which gate, which input goes in which gate. Okay, now if I choose S1 to be 1 and S0 to be 0, then the output is going to be C. So if I change C, as you can see, the output is C equal to C. When I change D, nothing happens. B, nothing happens. A, nothing happens. It only acts when C. So with these selectors, we choose which one of these inputs is going to be on the output. If I choose S0 and S1 to be 1, then the output is going to be equal to D. So here we have it. Change C, nothing happens, nothing happens, nothing happens. Okay, now here is a simple ICE integrated circuit called 74LS157, quad 1 of 2 data selectors. So here we have a binary input, 4-bit binary input. This is to the A, 1A. This one is 2A. This one is 3A, and this one is 4A. This is the pins of the multiplexer. Okay, and here you want on the third pin, this is 1B, here is 2B, here 3B over here, and 4B here. Here we enable the circuit, and here we have on the pin 15, if the input on the pin 15 is 0, then the gate will be enabled. If you have a bubble over here, it means that if the input here is 0, then it can work properly. If I put 1 here, then no matter what I do, no matter what I change here, here won't be here all on the output. It will be all zeros. Here on pin number 1, we choose which binary number are we gonna have on the output. If it is 0, it's the complement of 0A. It will choose this A binary number to the output. If this is 1, it will choose B. Let me demonstrate it. So enabled is okay because it is on low state because of this bubble. If there weren't no bubble here, then the enable you would have to click 1 to enable the circuit. But if you have a bubble, that inverts to the multiplexer, so you need just a low state, so you would make this circuit functional. Okay, now if I change this one, you will see I have 0, 0, 0, 1. 1A is 1, and I will have on the output 0, 0, 0, 1. If I change 1, 0, 0, 1, I will have here 1, 0, 0, 1, because 4A is 1, so the 4 epsilon is going to be also 1. 3A is 0, so the 3 epsilon will be 0. 2A is 0, 2 epsilon is going to be 0. 1A is 1, 1 epsilon is 0. But if I click here 1, you will see that this combination here is going to be the same as B. So if I put this one, you will see that I activated 3B, so the 3 epsilon is going to be 1. If I activate 3, 2, 2B, the 2 epsilon is going to be 1. So 0, 1, 1, 0, 0, 1, 1, 0. If I put a high state on the enable, you will see that all the outputs is going to be 0, and no matter what you do here, it won't change the output. So yeah, that was 74LS157. These are the pins. You can simulate this on Proteus. Okay, now here we have 8-line to 1-line multiplexer. Here we have the enable button. It always has to be on 0. And we have here a binary combinational logic. So if the combination here is 0, the output is going to be x0, which means that's the 0 binary number. When I change it to 1, you will see the epsilon is the same as x0, and this epsilon naught is just the complement of this epsilon. It is always different. These two combinations are always going to be different than each other. If I put 001 over here, you will see that x1 is going to be activated. See, if I click x, if I change the x1, then the output changes. If I want to change this one, it doesn't happen. On the output doesn't happen anything because we didn't select that input. We selected input number 2 or x1 because here is 001 is 1 in binary numbers, and you know x1 will be activated. So you see, if I want to activate the number 2, so I have to bring the combination 0 1 0, and x2 is going to be activated over here. So I change it like so. If I change the other ones, nothing happens because x2 is activated. If I bring number 3, the x3 is going to be activated no matter what I do with others. Only this x3 is going to be activated. So you see, if I change it to 0, the output is 0. This is the complement of that. If I change it to 1, the output is 1. Okay, now we have number 4. So number 4, x4, as you can see, do something else, nothing. If I bring number 5, x5 is activated. If I bring number 6, x6 is activated. If I bring 7, x7 is activated. If I bring a high state over here, nothing will, the epsilon will always show 0, and number 6 is going to show 1. So if you put a high state on enable, then it blocks the multiplexer. Now here I combine two 8-line to 1-line multiplexer. I combined these two 8-line to 1-line multiplexers to create a 16-line to 1 multiplexer. So now here I have a binary combination for here I can, if I have 4 bits, I will have I can go to the number 15. So when this 0 goes to the enable, this one circuit is activated, but here is blocked because we have a NOT gate, so high state is here. But if I bring on the enable 1, this one is blocked, and this one will work because here we have a low state. So now this particularly is the same as this particularly is the same as the last one we had here. The IC is called, sorry, I forgot to say, 74HC151. Okay, so here, if I have a binary combination of zeros, if I have a 0, then x0 here is going to be activated, and so the output here is going to be the same. Complements are not very useful for us, so we don't care about these complements. So if I put 0001, that goes to x1 over here, and it changes to x1, and so on and so on. x2, x3, you see that number 4, then x4 is activated, x5, 101 is 5, x6, and x7. But what happens if I put this here? Then this is going to be activated. So now we have a combination of this 1001, 1000 is number 8 in binary, so it will act on this particular input, because here we had 8 combinations from 0, 1, 2, 3, 4, 5, 6, 7. This is number 8 because it doesn't say number 8, but it just counts. After x7, you should imagine that this is number 8. As you can see, number 8 here, and this acts as number 8. So here you have it. That's why it is good to have enables, because we can combine more multiplexers to create bigger multiplexers with more inputs. If I bring a combination of 9, then this here is going to activate. This x1 on the second one acts as number 9. So it changes like this. If I bring number 10, this is a combination of 10, x2 acts here as number 10, so it changes only on this x2 on the second multiplexer. So you can combine more multiplexers to make a bigger multiplexer. So if this is number I think 11, here x3 acts as number 11. If I bring combination 1 1 0 0, that's number 12, and x3 here is going to be activated. If I bring number 13, then this one on x4 here, no, x5, sorry, this is x5 is activated. If I bring a combination logic of this is 14, then x6 here on the second is activated. If I bring a 15 combination here of 15, then you will see the x7 on this other one is activated. So this x7 acts and that's number 15. So, and if I want to bring other inputs here, nothing happens because those other inputs are not selected. So I think you learned about multiplexers. The biggest thing to know here is that you have multiple inputs and only one output, and you choose an input with these data selectors. Thank you for watching and see you in my next video. Goodbye.